Please again give a warm of applause for this seminar, and may this seminar will run well and also will be useful for every one of us. Amin. Distinguished guests, ladies and gentlemen, to commence this honorable program, we shall begin with the recitation of verses from the Holy Quran. We respectfully invite Mr. Ajib Atoha, the student of the Informatics Engineering Study Program, to deliver the recitation. For Mr. Ajib Atoha, the floor is yours.
Assalamualaikum warahmatullahi wabarakatuh. A'udzu billahi minasy syaithanir rajim. Bismillahirrahmanirrahim. Ya ayyuhalladzina amanu idza qila lakum tafassahu fil majalis idza qila lakum tafassahu majalisi fafsahu yafsahillahu lakum. Wa idza qila syuzu fasyuzu yarfa'illahu alladhina amanu minkum yarfa'illahu alladhina amanu minkum walladhina utul ilma darajat. Wallahu bima ta'maluna khabir. Bismillahirrahmanirrahim. إن هذا القرآن يهدي للتي هي أقوم يهدي للتي هي أقوم ويبشر المؤمنين الذين يعملون الصالحات أن لهم أجرا كبيرا وأن الذين لا يؤمنون بالآخرة أعتدنا لهم عذابا أليما ويدعو الإنسان بالشر دعاءه بالخير وكان الإنسان عجولا وكان الإنسان عجولا صدق الله العلي العظيم. السلام عليكم ورحمة الله وبركاته.
Thank you very much. The singing of the national anthem of the Republic of Indonesia Raya. All participants, please arise and sing together. witnesses, please be seated. Ladies and gentlemen, we shall now proceed to the welcoming remarks delivered by the Dean of the Faculty of Engineering, Wahid Hasyim University. We respectfully invite Dr. Imam Syafaat to deliver his address. Honorable Dr. Imam Syafaat, the floor is yours.
Assalamualaikum warahmatullahi wabarakatuh. Distinguished Rector of Universitas Wahid Hasyim, esteemed keynote speakers, respected colleagues, honored guests, and dear participants. On behalf of the Faculty of Engineering, Universitas Wahid Hasyim, it is my great pleasure to welcome you all to the International Conference on Informatics, Mechanical, Industrial, and Chemical Engineering, Icimice 2025, and the 15th Seminar Nasional dan Teknologi. Hadirin yang berbahagia, yang saya hormati Bapak Rektor Universitas Wahid Hasyim Semarang, Profesor Dr. Insinyur Helmi Purwanto STMT IPM. Para pembicara kunci yang kami muliakan, para kolega yang saya hormati, serta para tamu undangan dan seluruh saudara yang berbahagia. Di sini kami atas nama Fakultas Teknik Universitas Wahid Hasyim izinkan saya ucapkan selamat datang kepada seluruh hadirin di event International Conference on Informatics, Mechanical, Industrial, and Chemical Engineering, Icimice tahun 2025, sekaligus kegiatan Seminar Nasional Sain dan Teknologi ke-15 yang digelar oleh Universitas Wahid Hasyim Semarang. This joint conference, held on 10 December 2025, represents a vibrant collaboration between Universitas Wahid Hasyim, the Vocational School of Diponegoro University, and Cavite State University, Philippines. Together, we aim to foster dialogue, share knowledge, and strengthen networks that advance sustainable engineering and innovation for the benefit of society. We are deeply honored that today's agenda will be formally opened by the Rector of Universitas Wahid Hasyim Semarang, whose leadership and vision continue to inspire academic excellence and innovation. Allow me also to extend our heartfelt gratitude to our distinguished keynote speaker, whose insight will illuminate the path toward sustainable futures. Saya ucapkan terima kasih kepada para pembicara kunci yang hadir pada kesempatan kali ini. Our first speaker, Mr. Tirat Fakara Nukroh, PhD, from the Petroleum and Petrochemical College, Thailand, which will deliberate speech on the overview of decarbonization technologies in bioethanol production process. And our second keynote speaker, Dr. Engineering Muhammad Aziz from University of Tokyo, Japan. He will share his expertise on the carbon capture as a catalyst for circular innovation in industrial systems. And the last but not least, Ma Veronica P. Pena Florida from Cavite State University, Philippines. She will share her knowledge on the nature-inspired design and circular innovation, a new paradigm for sustainable engineering. This year, we proudly host 54 paper presentations, reflecting the dynamic contribution of scholars and practitioners from across Indonesia. Among the 20 participating institutions, Universitas Wahid Hasyim and Universitas Darussalam Gontor stand out as the most active contributors, submitting the highest number of paper. Pada kesempatan kami ini, kami bangga menyelenggarakan akan mempresentasikan 54 pemakalah yang tentu dari beberapa akademisi dan praktisi di seluruh Indonesia. Dari 20 institusi yang hadir, Universitas Wahid Hasyim dan Universitas Darussalam Gontor tercatat sebagai kontributor paling aktif dengan jumlah makalah yang banyak. We are also honored by the presence of extraordinary institutions from diverse regions of Indonesia, whose participant enrich the academic landscape of this event. Pada kesempatan ini, kami juga mengucapkan terima kasih atas partisipasi institusi dari seluruh Indonesia yang bisa saya sebutkan satu persatu, dari Politeknik Negeri Sambas, Universitas Teknologi Yogyakarta, UPN Veteran Jawa Timur, Universitas Tama Jagakarsa, Universitas Brawijaya, Universitas Riau, Institut Teknologi PLN, Universitas Diponegoro, Universitas Akprin Indonesia, Politeknik Negeri Jakarta, Institut Teknologi Kalimantan, Universitas Islam Indonesia, Universitas Trunojoyo Madura, Universitas Darul Ma'arif, Universitas Pasundan, Universitas Dian Nuswantoro, Universitas Al-Azhar Indonesia, dan dari Madrasah Aliyah Tahfidz Yambu'ul Quran Kudus. Their presence reflect the spirit of collaboration and the shared commitment to advancing science, technology, and sustainable development across Indonesia. Ladies and gentlemen, at this moment, with great respect, we kindly invite the Rector of Universitas Wahid Hasyim, Profesor Dr. Insinyur Helmi Purwanto STMT IPM, to officially open of the Icimice 2025 and the 15 Snst. Mohon berkenan Bapak Rektor Universitas Wahid Hasyim untuk membuka acara pada pagi hari ini. With that, I warmly welcome you all to this joint conference. May the discussion ahead be fruitful, inspiring, and impactful. Sekian, terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much for Dr. Imam Syafaat. And it's a great honor to invite the Rector of Wahid Hasyim University, Profesor Dr. Insinyur Helmi Purwanto STMT IPM, to deliver his welcoming remark and to officially open this program. Honorable Rector, the floor is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning and my praise and blessing upon us all. Om Swastiastu, Namo Buddhaya, Salam Bajikan Rahayu. Universitas, our international and national speaker joining us today, Mr. Red Fakaru PhD, the Petroleum and Petrochemical College Thailand, Dr. Engineering Muhammad Aziz from the University of Tokyo, Japan, Ma Veronica Pana Florida, Cavite State University, Philippines, and the Vice Rector, Dean, and Vice Dean, Head of Program Study, and all academic leaders. Dean of the Faculty of Engineering, Bapak Dr. Imam Syafaat STMT, and the entry committee team, all seminar participants, both on-site and online. Ladies and gentlemen, Alhamdulillah Rabbil Alamin. Adalah kita bersyukur kehadirat Allah Subhanahu wa Ta'ala. Kita masih diberikan nikmat kesehatan, kita masih diberikan kesempatan untuk dapat mengikuti program kegiatan yang diselenggarakan oleh Fakultas Teknik Universitas Hasyim. Let us offer our praise and gratitude to Allah Subhanahu wa Ta'ala for His blessing, health, and guides, enabling us to gather today for the important scientific event. The second International Conference on Informatics, Mechanical, Industrial, and Chemical Engineering, Icimice 2025, and Seminar Nasional dan Teknologi Snst yang ke-15. May peace and blessing also be upon the Prophet Muhammad SAW was in intercession. We hope for the after. Yang kedua, kami mengucapkan selamat dan apresiasi kepada Fakultas Teknik yang telah konsisten dan secara berkesinambungan menyelenggarakan kegiatan seminar, baik seminar nasional maupun seminar internasional yang kedua. Pada kesempatan kali ini kita telah menyelenggarakan 15 kali seminar nasional dan yang kedua seminar internasional. Ini merupakan sebuah prestasi yang dilakukan oleh Fakultas Teknik yang secara berkesinambungan dan secara rutin menyelenggarakan kegiatan akademik di Universitas Wahid Hasyim. This year, Icimice carries theme Innovative Engineering Approach in Envisioning Sustainability. This theme is particularly relevant to the global challenge. As the world countries to pursue innovative solutions to sustainability issue, decarbonization, energy transition, industrial efficiency, and environmental friendly technology. The role of scientific researchers, academicians, and engineers has become increasingly vital in shaping sustainable future. I hope that progressive idea, innovative research outcome, and meaningful academic collaboration will emerge, contributing significantly to develop of science and technology in Indonesia and global. Finally, saying terakhir dengan mengucapkan Bismillahirrahmanirrahim. I happy officially open the second International Conference on Informatics, Mechanical, Industrial, and Chemical Engineering 2025 dan Seminar Nasional Sain dan Teknologi yang ke-15 tahun 2025. May Allah Subhanahu wa Ta'ala bless and facilitate all activities throughout this event. Wallahu muwaffiq ila aqwamit thoriq. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Bapak Rektor, for the opening remark. Ladies and gentlemen, to conclude this opening session, we shall proceed to the prayer. We respectfully invite Mr. Pandu Wijaya to lead us in prayer. Dear Mr. Pandu Wijaya, the floor is respectfully yours.
Bismillah. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, please let us bow our head for a moment, pray to God Allah Subhanahu wa Ta'ala, so that our SNST and Icimice conference can be precious to all of us. I will lead this prayer based on the teaching of Islam, and those who are not Muslim, please, you are to pray according to each of your beliefs. Bismillahirrahmanirrahim. Biridha'illahi wa bi syafaati Rasulillahi sallallahu alaihi wasallam wa bi karamati awliyaillahi wa syuhada'i salihin wa ila khususan ila hajatina wa hajatikum sya'ulillahi lahumul al-fatihah. A'udzubillahi minasyaitonir rajim. Bismillah. Alhamdulillahi rabbil alamin. Iyyaka na'budu wa iyyaka nasta'in. Amin amin. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Hamdan yuafi ni'amahu wa yukafi mazidah. Ya Rabbana lakal hamdu kama yanbaghi li jalali wajhikal karimi wa 'azimi sultanik. Allahumma ja'al jam'ana hadha jam'an marhuman wa tafarruqna min ba'dihi tafarruqan ma'suman wa la taj'al fina wa la mina syaikinan wa la mahruman. Allahumma inni as'aluka ilman nafi'ah wa rizqan thayyibah wa amalan mutaqabbala wa qalban munawwara ya rabbal alamin. Ya Allah, today in this beautiful place we gather here to bring about an international conference. Make this conference as a useful science assembly, as a medium of sharing useful ideas, knowledge and experiences of scholars, researchers and students of various disciplines. May the conference we organize today benefit to our life, broaden our knowledge, shine our ideas, and lead us to be successful, productive persons, which in turn will boost dignity of our nation. Ya Allah, protect us from unintended temptation, show us the right path, and give us knowledge and strength to perform good things. Equally, show us and make it clear the bad things and give us knowledge and strength to avoid them. Ya Allah, you are the one who can fulfill our dua. Rabbana atina min ladunka rahmah wa hayyi lana min amrina rasyada. Rabbi israh li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Allahumma nawwir qulubana bi nuril hidayatik kama nawartal arda bi nuri syamsika abadan abada bi rahmatika ya arhamar rahimin. Wa sallallahu ala sayyidina Muhammadin nabiyil ummiyil wa ala alihi wa sahbihi wa barik wasallam walhamdulillahi rabbil alamin. Thank you. Wallahul muwaffiq ila aqwamit thoriq. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Dr. Pandu Wijaya, for the prayer. Distinguished guests, ladies and gentlemen, before continuing to the next agenda, we will proceed the photo session. We kindly invite the Honorable Rector, the Dean for other faculties, invited guests, and all the organizing committee to come forward to the stage for the on-site group photo session. And also for the participant joining the Zoom, kindly turn your camera on and prepare for the virtual group photo. Please come forward, all the participants. Kami persilakan kepada seluruh peserta untuk dapat maju ke depan dan juga untuk seluruh komite untuk bisa berfoto bersama. Bapak Dekan, silakan Pak. Iya, ya, sudah disebut dari tadi loh Pak.
Universitas Wahid Hasyim sebagai salah satu perguruan tinggi swasta yang berlandaskan Ahlus Sunnah wal Jamaah merupakan salah satu perguruan tinggi Nahdlatul Ulama terbaik di Indonesia. 24 tahun berdiri, Universitas Wahid Hasyim memiliki 25 program studi dari 9 fakultas. Fakultas Ekonomi dan Bisnis, Fakultas Pertanian, Fakultas Keguruan dan Ilmu Pendidikan, Fakultas Agama Islam, Fakultas Ilmu Sosial dan Ilmu Politik, Fakultas Teknik, Fakultas Hukum, Fakultas Farmasi, Fakultas Kedokteran. Sebagai universitas dengan jargon intelektual yang berkarakter, dengan bangga, Universitas Wahid Hasyim meraih banyak prestasi dari tingkat nasional hingga internasional, baik dari bidang akademik, olahraga, agama, dan seni. Fasilitas yang memadai membuat ribuan mahasiswa nyaman menuntut ilmu di Universitas Wahid Hasyim. Sarana prasarana yang lengkap menunjang pendidikan seluruh mahasiswa di universitas ini. Hadir untuk seluruh kalangan masyarakat, Universitas Wahid Hasyim menyediakan banyak beasiswa. UNWAHAS semakin dicintai mahasiswa dalam negeri dan luar negeri. Bentuk kepercayaan seluruh elemen lembaga dan instansi terhadap Universitas Wahid Hasyim, kerjasama dalam negeri dan luar negeri, terlaksana sebagai penunjang lulusan terbaik dan terampil. Inilah wajah Universitas Wahid Hasyim untuk Indonesia sebagai perguruan tinggi yang berani unggul menciptakan generasi emas Indonesia dengan pendidikan yang berkualitas dan berkarakter. Kami Nahdlatul Ulama, kami cinta Universitas Wahid Hasyim. Universitas Wahid Hasyim, Aswaja, muda mendunia.
This is where history, innovation, and commitment to excellence come together. From its humble beginnings in 1906 as an intermediate school, Cavite State University marks a new era of academic excellence. Under the strong and visionary leadership of the university president, Dr. Maria Agnes P. Nuestro, and top management, CVSU continues to advance sustained change and excellence grounded on its mission to serve through education, research, extension, and production. Offering 127 curricular programs, CVSU is committed to providing excellent education in arts, sciences, and technology. Our research and development centers pioneer sustainable solutions that impact the communities we serve. Guided by the values of truth, integrity, excellence, and service. We are relentless in our commitment to quality and innovation. From inclusive education to sustainable innovation, Cavite State University continues to rise, advancing sustained change and excellence for national development. Together, we ascend.
Ladies and gentlemen, we will now proceed to the main agenda of this conference, namely keynote speech session. This session will be guided by our honorable moderator, Ibu Dr. Indah Riwayati. Therefore, I would like to respectfully hand over the floor and the full guidance of this session to Ibu Dr. Indah Riwayati. Honorable moderator, the session is now entirely under your guidance. Thank you so much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Okay. Thank you very much for the time. Assalamualaikum warahmatullahi wabarakatuh. Good morning once again and warm welcome back all for our distinguished guests, speaker and participant joining us live via Zoom and UNWAHAS TV. We have been inspired by the opening remark, and now we move to the intellectual core of our conference, the keynote speaker sessions. Today we are immensely privileged to have three renowned experts who will share groundbreaking insight on our theme, innovative engineering approaches in envisioning sustainability. This session will be divided into two parts with dedicated discussion segment to allow for deeper engagement. To begin our first session, it's my great honor to introduce our first keynote speaker, an expert at the forefront of sustainable process engineering. Our speaker is a distinguished chemical engineer with a vast industry and academic profile. He held a PhD in technopreneurship and innovation management from Chulalongkorn University, a master with distinction from University of Manchester, UK, and is a licensed professional chemical engineer in Thailand. His career spanned over 15 years, including pivotal roles as process engineer and research leader at PTT Global Chemical, where he led innovative projects in polymer production, gas recovery, and reactor design, earning him several innovative awards. He later applied his expertise in bioprocess scale-up as the director of process design at food tech startup. Currently, he serves as lecturer at the Petroleum and Petrochemical College, Chulalongkorn University, and recently managed the Biocircular Green Economic Technology and Engineering Center, BCGTEC, overseeing multi-million baht project on CO2 utilization and carbon capture technologies. He is also a certified greenhouse gas professional. With a strong publication record in decarbonization and process system engineering, he is perfectly positioned to guide us today. Joining us from Bangkok, Thailand, please welcome Dr. Trirat Fakanaruko. Dr. Trirat will present on the crucial topic for our sustainable future, overview of decarbonization technology and bioethanol production process. Let's give him one virtual applause. The floor is you, Dr. Trirat. Please.
Thank you, everyone. So let's share the slide. So, good morning, our distinguished guests and participants. First of all, let me thank the ICIMICE organizing committee that invited me to speak today. It is my honor to be here today. My name is Tirat Vacharanukra. I am a lecturer from the Petroleum and Petrochemical College, Chulalongkorn University. And today, I will give a talk in the topic of overview of decarbonization technologies in bioethanol production process. The aim of this talk is to provide the clear and concise overview for the decarbonization strategies that can be applied in bioethanol production process. Climate change became the world's most urgent crisis that everyone need to pay attention. The global carbon dioxide emission rose from 13 gigaton in 1970 to 37 gigaton in 2024. And the year 2024 became the first calendar year that the Earth's mean surface temperature surpassed 1.5 degrees Celsius above pre-industrial average. Among all the causes of carbon dioxide emission caused by human, transportation sector is the main sector that contributes. It is responsible for nearly a quarter of global carbon dioxide emission. And biofuels become an important solution to solve the climate change. Biofuels produced from the biomass that absorb carbon dioxide from the atmosphere via the photosynthesis can be the much greener alternative compared to the conventional fossil fuel. And bioethanol is the most widely used biofuel, contribute to 62% of market share, and following by biodiesel with 26% market share. The production scale of bioethanol is very large. The 120 billion liters of bioethanol is produced globally every year, leading by USA and Brazil. Not only application in the road transport, bioethanol can also serve in many ways for the green and sustainable solution. It can be converted to sustainable aviation fuels via the alcohol to jet pathway to serve the aviation industry, which contributes about 2% of global emissions. It can be a very versatile chemical intermediate that can turn to different kinds of green chemicals. For example, we can use bioethanol to produce bioethylene, which is a base chemical for petrochemical sector. The bioethylene can reduce emissions of carbon dioxide by 2.1 kg carbon dioxide per kilogram compared to fossil ethylene. Moreover, we can use bioethanol as a liquid hydrogen carrier. The bioethanol can be transportation in liquid form and transformed to hydrogen product with a byproduct such as potassium acetate that can be used as a fertilizer. So let's take a look at the evolution of bioethanol production. There is a long history of evolution in bioethanol production process. Start from the first generation of the production process that we use food crops as raw material to produce bioethanol. Although this generation is the most widely used production process nowadays, it still have many concerns in the competition with the food source for human. So the second generation of bioethanol production process is developed. In this generation, we use the biomass that is non-food. For example, we can use lignocellulosic materials to be a feedstock to convert to bioethanol. However, this generation of bioethanol production also have some challenge. It has quite a complex process in pretreatment, and the pretreatment process of lignocellulosic materials is an energy-intensive process that requires high operating costs. So we turn to the next generation in bioethanol production, the third generation. In this generation, we apply algae to be the source of the feedstock with the advantage of algae that can produce high yields of carbohydrate and can significantly lower the land used for cultivation. Algae become the interesting alternative to be applied at the bioethanol feedstock. But this generation also have some challenge in the investment cost and scalability. And the latest generation of bioethanol production is the fourth generation that we apply advanced biotechnology to engineer the microbes to improve their efficiency to produce and accumulate carbohydrate and have the higher ability to transform those substances into ethanol. Some research can even engineer the microbe so they can be able to turn the carbon dioxide directly to ethanol. Although there are many alternatives and generations in ethanol production process, most of the process share a similar product scheme. We start from the biomass that we use as a feedstock and then send it to feedstock pretreatment, where we turn those biomass into the sugar substrate. Next, the sugar substrate is sent to the fermentation system. In this system, we use the microbes to turn the substrate into ethanol via the fermentation process. And then we obtain the fermented liquid that can be sent to the purification system, which we normally use the distillation columns to purify the ethanol and separate water and all the impurities from the fermentation product. Finally, we obtain the purified ethanol as the final product of the process. In addition, the biomass residue from the feedstock pretreatment can be sent to cogeneration system, where we use the combustion process to produce energy source, including electricity and steam, to supply the main process flow. The surplus energy from the cogeneration system can also be sent and export to outside. From this process diagram, we can see that there are two main sources of carbon dioxide emission. The first spot is at the fermentation system, where we generate fermentation carbon dioxide as a co-product in the fermentation process. And the second spot of carbon dioxide emission is at cogeneration system, where the carbon dioxide is generated from the combustion process. With these two main points, carbon dioxide emission, it causes bioethanol production process to be, we cannot call the bioethanol production process to be fully green and sustainable process, because the carbon dioxide produced from this process can be ranged from 0.19 to 2.08 kilogram carbon dioxide per liter of ethanol production. If we can mitigate all of these emissions in bioethanol production process, we can turn bioethanol from the low carbon fuel to the carbon negative fuel to be our future solution of the climate change. So there are several strategies to decarbonize the bioethanol production process, and we have categorized those strategies into three main pillars. The first strategy is the process optimization, where we improve the efficiency of the process of production bioethanol to have higher efficiency, higher ethanol yield, and reduce energy consumption. The second strategy is to apply carbon capture and utilization, which we can turn our carbon dioxide emission into higher value product and get additional revenue stream from the new product. The third strategy to decarbonize the bioethanol process is the carbon capture and storage, where we send the remaining part of carbon dioxide to underground to storage for a long term. And next, we will go deep into the detail of these three strategies one by one. Let's beginning with the first strategy, which is the process improvement. To improve the process of bioethanol production, we can take a look in many major parts of the process system in the production of bioethanol. Let's begin from the feedstock pretreatment. There are currently there are many technology that can apply and improve the feedstock pre-treatment process. For example, there are a research that try to apply the membranes in the process of sugar concentration instead of using evaporation process. So we can reduce a large amount of energy consumption in this step. Next, for the fermentation system, we can develop thermotolerant microbes that allow us to do the fermentation at higher temperature and reduce the need for cooling loads that we supply to the fermentation system. There are also many new fermenter design and configuration that can improve the yield of ethanol, so it will reduce the amount of carbon dioxide emission per kilogram of ethanol produced. Next, let's turn to the product purification system part. In this system, to purify the bioethanol, we need a high energy intensive distillation system. So we can turn from this conventional distillation system to the integrated heat integration distillation. For example, we can apply the multi-effect distillation system that reduce the pressure of the distillation to reduce the boiling point of ethanol. And then we can also turn the energy from the condenser of distillation column to apply at the reboiler of another distillation column. This can reduce steam reduction in the distillation system significantly, up to 63%. And last but not least, it is the cogeneration system where we apply the biomass residue to turn it into energy for the process. This cogeneration system is the main part that emits the carbon dioxide to the atmosphere from the combustion. There are currently several technology alternatives to improve the efficiency and reduce the emissions of cogeneration process. For example, BIGCC is the process that we replace the biomass combustion with the gasification process to turn out the biomass into the syngas that can convert to energy with much higher efficiency and lower carbon dioxide emission. With all of those technology, we can turn the bioethanol production process into the process that have low carbon dioxide emission and low energy consumption, and also improve the sustainable and efficiency of the process in the same time. Next, let's move on to the second strategy of decarbonization bioethanol process. In this part, we will talk about carbon capture and utilization technology. The bioethanol production process have a unique advantage because the carbon dioxide that emit from the fermentation system have very high purity, more than 90% of carbon dioxide in the emission stream. So we can utilize this purified carbon dioxide directly without any purification, or we can do further purification to meet the specification with only minimum cost of the purification process. In addition, the bioethanol production also also have the cogeneration unit, so it can produce energy including electricity and steam by itself and have some surplus energy to export, we can use this energy to supply the carbon capture and utilization system that quite an energy intensive process. So in terms of carbon capture and utilization, there are many opportunities to convert carbon dioxide from the bioethanol production process into many valuable products. We can use the carbon dioxide directly in the beverage and food industry, or we can turn those carbon dioxide into sustainable aviation fuel or SAF. And we can produce many chemicals from carbon dioxide, including methanol and succinic acid. Some research even apply the surplus energy to the electrolysis process. So the electrolysis can produce the hydrogen raw material that is the important raw material to supply into the carbon dioxide utilization reaction. For example, hydrogen can react with carbon dioxide to form the methanol product. Although there is many interesting alternatives in these strategies, the investment of carbon capture and utilization still requires high investment cost, and the technology level readiness is still not very high. So it still requires the support from the R&D research and from the policy to improve the advancement in this field. Now, let's move to the third decarbonization strategy, which is carbon capture and storage. In this strategy, we can turn the remaining carbon dioxide from the fermentation and post-combustion at cogeneration. We can send it to the compression system to compress and send through the pipeline transport to inject it underground to store it for a long time. We can also apply this method to the enhanced oil recovery system, so we can help to extract oil from the oil well at the improved extraction rate. This method of the carbon capture and storage also need high energy cost. It spent about 74% of power to allocate to carbon capture and storage, and needs quite high capital investment, about 5 times of the norm compared to the base case of conventional bioethanol production. So the feasibility of the carbon capture and storage still mainly rely on the oil price that it can recover, and also rely on the carbon price that can use for subsidize of the cost of the process. However, compared to carbon capture and utilization, the carbon capture and storage have quite higher technology readiness level. There are many demonstration and operating sites of carbon capture and storage that apply with bioethanol plants around the world, including in the USA and in Canada. So, in summary, we can combine all the three strategies of the bioethanol decarbonization process together. First of all, we can look into the process improvement of the process by improve all the steps of the process unit to reduce energy consumption, and reduce carbon dioxide emission that emit directly from the process. Then, after we do the improvement, we can turn to the second strategy. In this strategy, we send the remaining carbon dioxide emission from the process to the carbon capture and utilization to turn them into the valuable product and turn them to the additional revenue streams for the business. After we apply the utilization of carbon dioxide, we can send the remaining part of carbon dioxide that cannot be utilized to storage underground via the carbon capture and storage. So we can storage the remaining carbon in the long term with the chance to do the enhanced oil recovery. Looking into the future, there are a lot of opportunities for the improvement in all these three strategies to improve the decarbonization of the bioethanol process. The first one is the advancement of carbon capture and utilization technology. There are many technologies that in the developing phase, including membranes, enzymes, and electrochemicals. We can apply all of this technology in the future to improve the process of carbon capture and conversion to be more efficiently and have lower investment costs. The second one is the process intensification, where we apply the knowledge of process engineering to design the modern unit equipment and combine the function of different unit operation together. And we will result in the high efficiency unit operation that have lower investment costs and also lower the operating costs. The next thing is the development of the third and fourth generation of bioethanol. These two generations of bioethanol are now developing rapidly, and we expect to see this technology to be commercialized with the advantage of the high ethanol production and more environmentally friendly result. The next important thing is the support from the policy and carbon market mechanisms. Of course, to expedite the carbon dioxide utilization and storage and decarbonization process to be commercialized faster, we need a subsidize from the government policy and carbon market trading scheme in order to support and subsidize the cost of investment and operation of this technology. The final things that can help improve the technology in this field is the renewable energy, that we can further integrate many different kinds of renewable energy source into the bioethanol production system and the carbon capture and utilization system to support the high energy intensive process of this process. With all of this development in the near future, we expect that the bioethanol production process will become ultra low carbon emission or even carbon negative emission process in the near future. These three strategies, including process development, the carbon capture utilization, carbon capture and storage, not only not only applicable for bioethanol production process, but this framework can extend to other chemical industries that is carbon and energy intensive. We can apply all of these strategies to reduce the carbon dioxide emission in all chemical industry and improve the various industrial process toward the cleaner and more sustainable production. All the content from this presentation is a part of collaborative work by an expert team showing in this list, and full technical details and reference are available in the research article shown in this page. From all of you, and now let's turn to the Q&A session. If you have any question or suggestion, please feel free to discuss.
Urgent global need for decarbonization. We will now open the floor for discussion. To our audience, this is your opportunity to engage. Please submit your question for Dr. Trirat via question and answer box on your screen. I think we have time for 2 or 3 questions. While the participant formulated the question, allow me to begin, Dr. Trirat, for a question.
Okay.
Thank you. Given your extensive experience in scaling technology from lab to industry, what do you think see as the most significant non-technical barrier, be it economic, regulatory, or supply chain, to implementing this decarbonization technology in Southeast Asia, especially Thailand? I think the problem will be different between Thailand and Indonesia. And how can it be overcome? That's my question. Thank you.
Thank you for the question. So now there is many challenge in development of carbon utilization and storage technology. First of all, we need to improve more technology readiness level of the carbon utilization technology so it can be applied in the commercial scale. Now we have many ideas and many research in this area, but most of them in the research laboratory and the pilot scale. So we need to take more effort to develop this technology to be commercialized. And for the carbon capture and storage, one of the main challenges is how to transport and collect the carbon emissions from different sources in the different area of the countries and combine it together to inject into the underground geological sites. This needs a lot of infrastructure investment, and so it needs government to involve to implement this project, and many companies and industries need to join together to plan and design this infrastructure to use in a long term.
Okay, thank you very much for the answer. It's not only technology, but also how to apply it in the industry and the real sector, right? Okay, maybe the next question from the chat box. I will try to, there are some questions, doctor. It's okay. I think there are 3 questions from, maybe the first question I will read for you. This is from Nur Hidayat, Mechanical Engineering UNWAHAS. He has a question. From the point of view of the economic analysis, which bioethanol generation that is the cheapest one? This is.
Okay, thank you for the question. As I talked, there are many different generations of bioethanol feedstock, but nowadays the most widely used bioethanol production, I think more than 90% of bioethanol produced from the first generation feedstock that we apply the food crop as the raw material. And this generation is the technology that have a lowest investment and operating cost because it's a long-term technology that have been developed to fully commercial for a long time. For other technologies in bioethanol production process, it still needs more development to make it to be feasible in commercialized sector. This includes the cellulose conversion to bioethanol that still have very high cost to turn those biomass residues into the fermentable substrate. And also the algae technology still have high cost for cultivation facility investment and the cost for feedstock pre-treatment to separate the water from the algae. Finally, the fourth generation bioethanol production is still underdeveloped, and we need to be sure that all the process of engineered microbe are under the correct regulations and not be harmful to the environment.
Okay, thank you. Thank you very much, Doctor. And the next question is from Feby, Mechanical Engineering UNWAHAS, implementation of fourth generation of bioethanol. This is her question.
Okay, thank you for the question again. And as I told earlier, so the fourth generation of bioethanol production utilize the advanced biotechnology to engineer the microorganism to improve their ability to produce more fermentable substrate, and also to improve the ability of those microorganisms to convert those substrate into ethanol. However, the challenge of the fourth generation is that advanced biotechnology is start from the lab. So after we have some successful results in the laboratory, it still need time to scale up and see the effect that how this microbe can perform in the larger scale, and we need to adjust the process equipment to be suitable to the unique characteristic of different microbes. And one more concerning issue is about environment. If we engineer the microbe and this microorganism get out to the environment, do they will make any harmful impact to the environment? So we need to apply the good control procedure and to be sure that everything will not have unacceptable damage to impact our world.
Thank you. Yes, thank you, Dr. Trirat. I think this is about it's not the scale-up process, but also the microbe problem that's used in this process. That's right. Okay, for the next question, still have maybe, there are so many questions, I think. 1, 2, 3, this is 2. Okay, next question is from Shaila, Chemical Engineer UNWAHAS. This is, as we know that ethanol water system is azeotropic, is there any advanced technology in the purification system? How to separate between the ethanol and water in azeotropic?
Okay. So,
please.
Ethanol and water system is as Silas told in the chat, it is a azeotropic process. So at the we can improve the purity, certain concentration, and after that, it will be very difficult to further purify ethanol to the high purity. So we have to help us to break the azeotrope point. For example, we can apply some solvent to change the volatility of the ethanol and water, or we can use some material to absorb the water from the mixture instead of using distillation technique. But as long as I know, all of these techniques have been used for quite a long time, and I think that there should be some new development in this field. But in my knowledge, I am not sure that there will be other new alternative in the near future or not.
Yes, okay. Thank you. We can use some kind of extraction or adsorption process. That's right, doctor. Yes. For the next question, this is one, two, three. Two more questions. Is it right? Is it okay, doctor?
Okay.
Two more
sure.
questions. Okay. This is from Abil, Informatics Engineering UNWAHAS. Lignocellulose is considered one of the most promising raw material sources for bioethanol production. However, from technical perspective, the production process of bioethanol from lignocellulosic material is relatively complex. Please kindly explain whether lignocellulosic biomass has been used for commercial scale bioethanol production. Yes, he asked about the commercial plan, maybe. This is.
Thank you. So currently there are many effort to develop the commercial scale of the process to turn the lignocellulosic material into the bioethanol. But as I know, especially in Thailand, we also developed it in the pilot scale and try to improve the process in terms of the operating cost and reduce the complexity of the way we turn those lignocellulosic materials into fermentable sugar. So I think in terms of commercial, it still have need some more development to make it feasible in the large scale. And nowadays we can see many research and effort around the world to improve this field of technology.
Okay, so in Thailand is still in pilot plant scale, right? This is.
Yes.
Okay. Okay, for the maybe last question, doctor. This is from Ilma, Chemical Engineering, UNWAHAS. In the presentation, it was mentioned that one method to improve bioethanol production is the use of membrane technology instead of conventional evaporation. Please explain under what condition membrane can be applied. Can membrane technology be used directly for the product stream coming out of the fermenter?
Okay, thank you. So membrane technology is very interesting alternative that can use for purification system, because we can avoid the process that consume a large amount of energy. In terms of feedstock pre-processing process in bioethanol production, when we convert the biomass into the fermentable sugar, including mainly glucose, sometimes the solution, the liquid that we obtain from this process is in the very low concentration, and it will not suitable for direct fermentation. So we need to apply some process to increase the concentration of those sugar into the proper level for microbe to turn it into the ethanol via fermentation process. So for this reason, we normally use the evaporation process to evaporate the water out and increase the concentration of sugar. Membrane technology become another alternative that we apply to separate water from the sugar substrate to increase the concentration without apply any heat. And as mentioned in the question, this membrane technology can be applied in many applications of purification process, including for purification product stream. We have a membrane that can separate impurity and water from ethanol. There is many research ongoing in these fields. However, there are still some challenges for apply membrane technology in the commercial level. This includes the lifetime of the membrane material and the problem of fouling, because after we use membrane with the liquid that not clean enough, the fouling of the impurity can turn the membrane to can reduce the permeability of membrane and reduce its efficiency.
Okay. Fascinating. Thank you for that clarification, Doctor. We must unfortunately pause the discussion here, I think. Yeah, once again, thank you to Dr. Trirat Fakanuro for a fantastic introduction to our keynote speaker. Yes. Okay, thank you very much, Dr. Trirat. Yes.
Thank you. ขอบคุณครับ
Give applause for our speaker. Take a break for about 5 minutes. After that, we will continue to the next keynote speaker. Thank you. Morning, Madam
Am I
Fanny.
I'm sorry, I recently lost my connection. So am I audible right now and am I visible?
Okay, you are visible now. That's okay. Your
So
face is okay.
can I start my presentation?
Wait for I will open this session first. Okay, thank you.
Okay.
Madam Anita.
Sure.
Okay.
I thought it's already my turn.
Hi.
Thank you.
Thank you. We now proceed to our second session where we will come to more distinguished speaker. Minute. This is our second keynote speaker is bring a foundational and biocentric physiology to sustainability. She is an accomplished academic leader and administrator from Cavite State University in the Philippines. She holds a PhD in biology from the La Salle University, where she conducts pioneering research. Currently, she serves as director for international and local collaboration and linkage, and the officer in charge of graduate school at her university. Her research interests are deeply rooted in ecological conservation and sustainable development, and she is a recognized expert in organization efficiency and quality management. Beyond her administrative and research role, she is passionate advocate for community service and environment sustainability. Her unique interdisciplinary background allows her to bridge biology, management, and engineering principles. Please help me give a warm welcome to Prof. Ma Veronica P. Pena, Florida. Give applause, please. Virtual applause. Thank you.
Thank you so much, ma'am, and it's nice to see you. Hi,
Nice to meet you too.
good morning, everyone.
Good morning.
So I'm ready to start with my presentation. So I've prepared a video presentation for you, but before that, allow me to introduce my topic.
Okay.
So again, good morning to everyone present here at the International Conference on Informatics, Mechanical, Industrial, and Chemical Engineering. It is my honor to be here in a brilliant gathering of researchers, educators, and innovators committed to shaping the future of engineering. I extend, of course, my heartfelt gratitude to the Faculty of Engineering of Universitas Wahid Hasyim for the invitation and for creating this vibrant space for interdisciplinary learning, collaboration, and discovery. So as a biologist, I spend much of my time observing the nature's quiet genius, how organisms build, adapt, heal, regenerate, and sustain themselves. In biology, nothing is wasted. Every structure exists for a purpose, and every process is optimized for survival. And every system is interconnected. In contrast, our human-made systems, especially in engineering and industrial production, have historically operated on a very different logic. Exact, produce, consume, and dispose. This linear model has fueled impressive progress, yes, but has also led us to a point where resource scarcity, climate instability, and waste accumulation are now unavoidable realities. So today, my role is to invite you to look at engineering through the lens of biology, through the lens of systems that have been refined by 3.8 billion years of research and development. Nature is not just about a source of inspiration, it is a library of solution. And with that, may I request tech team to play my recorded video. Thank you.
Yes, thank you. Okay, after Prof. Fanny introduce her presentation, after that we will watch her video, her presentation video now. The virtual floor is you, Professor, please.
Good day, everyone. Today I'm here to present the topic Nature Inspired Design and Circular Innovation, a New Paradigm for Sustainable Engineering. I am Maria Veronica. Good day, everyone. Today I'm here to present the topic Nature Inspired Design and Circular Innovation, a New Paradigm for Sustainable Engineering. I am Maria Veronica Peña Florida, the Director for International and Local Collaboration and Linkages Office of Cavite State University. Let's be honest, engineering today isn't the same as engineering 20 or even 10 years ago. The world is changing fast. We're dealing with shrinking resources, increasing waste, and technologies that are becoming outdated just as quickly as we build them. And on top of that, we're seeing the real effects of climate change on our roads, buildings, and the entire cities. For a long time, industries followed the same pattern. Take materials, make something, use it, and then throw it out. It worked for quite some time, but not anymore. We're simply running out of space, resources, and time. And this is where you future engineers come in. Everything you design, gadgets, machines, buildings, system has actually an impact. The challenge now is how do you keep innovating without breaking the planet in the process? When we look at the world today, it's clear that the environment engineers are working in it's very different from what it used to be. First, we're dealing with increasing resource scarcity. Materials we once thought were abundant, like certain metals, minerals, and even fresh water, are now becoming harder and more expensive to obtain. At the same time, waste and pollution are rising faster than we can manage them. Then we have the climate change, which is no longer just a scientific concept, it's something engineers must now design around. So, with these pressures, good day, everyone. Today I'm here to instead we need designs that use fewer resources, generate less waste, and can adapt to the realities of the changing climate. This shift isn't just necessary, it's an exciting opportunity to rethink how we build, design, and sustain the world around us. Traditionally, most industries have followed a very simple model. Take resources, make a product, and then throw it away. That's the classic linear system. It worked during the time when resources seemed unlimited and environmental impact wasn't a major concern. But today, the model is short sighted and honestly no longer realistic. This is where the circular thinking comes in. Instead of designing things with an endpoint, we designed them with a longer and smarter life cycle. In the circular system, we ask, can this product be reused? Can parts be repaired? Can materials be recycled? Can the system generate instead of deplete? Thinking of it as the designing products the way nature does. In nature, nothing comes waste. Every output becomes an input for something else. For engineers, this shift from linear to circular isn't just an environmental idea. It's a design challenge. How do you make machines, devices, buildings, or systems that stay in use longer, are easy to fix, and don't need end up in mountains of trash? So the move to circular thinking isn't just about being eco-friendly. It's about being smart, efficient, and future ready. It's the kind of mindset that will define the next generation of engineering. The second topic is on nature-inspired design, or what we call biomimicry. So what is the nature-inspired design? When we talk about the nature-inspired design, or what we call biomimicry, we are really talking about the learning from the best engineer with natural systems, organisms, and the entire ecosystems have been solving problems through evolution. Nature has perfected efficiency, resilience, and adaptation and balance long before humans ever existed. So in engineering, instead of reinventing the wheel, when you need to study how plants, animals, and natural processes work. How does a leaf maximizes energy capture during photosynthesis? How do termites regulate temperature? How do spider webs activate strength and flexibility at the same time? So nature-inspired design means taking these biological strategies and translating them into solutions for human challenges, whether it's developing stronger materials, smarter structures, or more sustainable technologies. It's about treating nature as a mentor and allowing its time and tested wisdom to guide modern engineering innovations. So what are the biomimicry's core principles? The first one is when we look closely on how nature works, we find a set of principles that are beautifully simple yet incredibly powerful. First, the nature runs on sunlight. It relies on abundant renewable energy. Imagine if our technologies were designed with the same mindset. Second is that nature also uses only the energy it needs. There's no excess, no unnecessary consumption. Every process is efficient and purposeful. Then there's the idea of fitting from form to function, such as the bird's wing, a seashell, a honeycomb. Nothing is random. The shape always supports its function. Perhaps one of the nature's most interesting strategies is that recycling everything. Waste doesn't exist in ecosystem. Everything becomes an input for something else, and instead of promoting competition alone, nature rewards cooperation. Thinking of symbiotic relationships and entire ecosystem built on mutual support. Finally, the nature constantly adapts and evolves. It learns, adjusts, and improves over time. These principles aren't just poetic, they are actually practical. When applied to material design, product engineering, architecture, or even systems thinking, they push us to create solutions that are sustainable, resilient, and aligned with the way life has always thrived on our planet. What are some examples of real engineering in terms of biomimicry? The first one is Kingfisher-inspired bullet train. So one of the most famous example of the nature-inspired design comes from Japan Shinkansen bullet train. So engineers were facing a serious problem. Every time the train exited a tunnel at high speed, it created a loud sonic boom that disturbed nearby communities. So the solution didn't come from another machine, but from a bird. The design team looked at the kingfisher, a bird known for diving into water at high speed without making a splash. Its long, sleek beak cuts through the air and water smoothly, and inspired by this, the engineers reshaped the train's nose to mimic the kingfisher's beak. The result was actually incredible. The redesigned train eliminated the tunnel boom and significantly reduced the noise. Even improved aerodynamics, which led to better energy efficiency and faster speeds. By observing a single bird, engineers solved a complex engineering challenge proving how powerful nature-inspired design can be. The next one is lotus leaf self-cleaning coating. So another amazing example of the nature-inspired comes from something as simple as a lotus leaf. If you've ever seen a lotus in a pond, you'll notice that its leaves always look clean, even though they live in muddy water. So scientists discovered that the leaf has a special micro-nano texture on its surface. Instead of being smooth, it's covered with tiny bumps that prevent water and dirt from sticking. So when water lands on the leaf, it forms perfect beads that roll off, taking dust and contaminants with it. This is known as the lotus effect. Engineers replicate this structure to create self-cleaning coatings used in paints, solar panels, fabrics, and even glass windows. These coatings help surfaces stay clean longer, solar panel where dust can reduce efficiency. So from a single leaf, imagine, we gained a smarter way to keep surfaces clean without chemicals, constant washing. It's a powerful reminder for us that nature's design are not only elegant, but incredibly practical. Okay. One of the most important and fascinating examples of biomimicry comes from something we usually overlook: termites. In hot climates such as Africa, termite mounds stay remarkably cool inside. Even when outside temperatures soars, still their their mound are very cool. So how? Termites build intricate tunnel systems that allow air to circulate naturally, constantly pulling in fresh air and pushing out warm air. It's nature's own air conditioning system. So architect Mark Pierce studied this phenomenon and applied it to the design of the Eastgate Center in Zimbabwe. So instead of relying heavily on mechanical air conditioning, the building uses a network of vents and chimneys modeled after the termite mounds to regulate temperature. The result is quite amazing. The building stays comfortable throughout the day, using up to 90% less energy than conventional structures. It's a perfect example of how observing nature can inspire sustainable architecture that reduces energy consumption, lowers cost, and creates healthier indoor environment. From tiny termites, we learned how cool massive buildings and no machine required. Another brilliant example of nature shaping modern engineering comes from humpback whale. Despite their enormous size, humpback whales are incredibly agile in the water. Scientists followed that their flippers have unique bumps called tubercles along the leading edge. The bumps held reduced drag and increased lift, allowing the whale to maneuver gracefully. Engineers took this idea and applied it to wind turbine blades, wherein traditionally these blades were designed to be smooth, but when researchers added similar bumps along the leading edge, just like on the whale fins, the performance changed dramatically. The blades were able to catch more wind at various angles, especially at lower speeds. The impact was significant. Turbines with this biomimetic design became up to 20% more efficient. That means that more renewable energy produced with the same wind and quieter operations too. It's a powerful reminder that sometimes the smartest engineering solutions aren't found in a lab, but in natural world perfected over a million of years. Then we have something tiny but very, very powerful. It is the compound eyes of the insect. So unlike humans who see through a single lens, insects like dragonflies and flies have thousands of these tiny lenses arranged in a curved pattern. So this gives them an incredibly wide field of view, allowing them to detect motion from almost any angle. Engineers and scientists have used this natural design to create advanced camera system by using 3D printed curved sensor array that mimic the structure of insects' eyes. Researchers have built cameras that are smaller, lighter, and capable of being far more than the traditional flat sensors allow. So these innovations are now being used in surveillance systems, medical endoscopes, and robotics, where panoramic and precise visual is very, very crucial. So the results are impressive. Cameras inspired by insect eyes can achieve panoramic vision with virtual and no distortion. So that means clear images, better motion tracking, and wider coverage. All thanks to the design followed directly from the nature's miniature vision experts. And then considered as one of the most elegant engineering lessons from nature comes from the humble beehive. Bees instinctively build their honeycombs using perfect hexagonal cells. And this shape isn't actually random, while proving maximum strength. In other words, bees discover the ideal balance between durability and resource efficiency long before humans did. Engineers saw this and began applying the same principle to the modern design. Today, honeycomb structures are widely used to create lightweight yet extremely strong panels in fields like aerospace, packaging, transportation, and architecture. Airplane wings, spacecraft components, and even impact-resilient packaging all rely on this hexagonal structure to reduce weight without compromising strength. The impact is huge, actually. Lighter material means lower cost, improved performance, and reduced energy use. Whether it's helping aircraft fly more efficiently or creating stronger building materials, the honeycomb pattern continues to prove that nature's geometry is not only beautiful or aesthetic, but brilliantly optimized for real-world engineering challenges. Okay. The last subtopic to be discussed is circular innovation. So what is circular innovation? So when we say circular innovation, we are actually talking about reimagining the entire life cycle of a product. From the moment it's designed to the moment it is retired. That's why it's called circular. Instead of the traditional linear mode or linear process, which I have discussed earlier, which is the take, make, and throw away, the circular innovation focuses on keeping materials in use for as long as possible. The first one is that it starts with durability. So designing products that would actually last. Then we think about repair. Repair, making sure that things can be easily fixed instead of replaced. The next is reuse, finding ways for products or components to have a second life. And when something truly reaches the end use, remanufacturing allows us to rebuild and upgrade it. And finally, recycling ensures that the raw materials can re-enter the system, um, So the goal is simple but powerful. We need to minimize material extraction and reduce waste. By closing the loop, we not only conserve resources and cut pollution, but we also inspire more sustainable business models and smarter engineering solutions. So circular innovation shifts us from a disposable mindset to one where materials continuously flow and value is preserved. What are the key pillars of circular engineering? So when we talk about circular engineering, we're talking about a shift of mindset from designing product that end up waste to designing system that continuously generate value. There are four key pillars that guide this approach. The first one is is the design out waste. So instead of treating waste as an unavoidable byproduct, circular engineering asks us to eliminate it from the very start or from the very beginning through smarter material choices, modular designs, and efficient processes. The second is keeping materials in use. So this means creating products that can be reused, repaired, upgraded, or remanufactured so that materials stay in circulation instead of being discarded. Third is we have regenerate natural system. So circular engineering doesn't just reduce harm, it aims also to restore. That includes using renewable resources, supporting biodiversity, and allowing ecosystems to recover as part of the product cycle. So, and finally, the end product lifetime. By designing for durability and long-term performance, we reduce the need for constant replacement, saving both resources as well as cost. So together, these pillars help us build systems that are not only sustainable, but smarter, more resilient, and aligned with the nature itself and aligned with the way nature itself operates. Okay. So what are the circular engineering strategies? When we shift toward circular engineering, we don't just redesign product, we redesign the entire system per se. There are 5 key areas that help make this shift practical and achievable. The first is modular design. This means building products in parts or modules that can be replaced, upgraded, and repaired individually. It extends products' life and reduces waste because you don't have to throw out the whole system when one part fails. Then we have materials recovery. At the end of the product's life, we extract value materials such as metals, plastics, fibers, so that they can be reprocessed and used again. This reduces the needs for virgin sources and lower environmental impact. The third strategy is the product service system. So instead of owning products, users access services like bike sharing or leasing appliances. So this encourages companies to design longer lasting items because they maintain ownership and responsibility. The fourth one is that we have industrial symbiosis. So this is where waste from one industry becomes a useful impact input for another. It creates networks of businesses that share resources, energy, and materials, boosting efficiency and reducing waste across the entire region. And finally, upcycling technologies, where these transform waste into products of higher value, like turning plastic bottles into fabric or converting food waste into bioplastic. So together, these strategies help us build a circular system where materials continuously flow, products last longer, and engineering contributes to a more sustainable future. So what is the new paradigm? So in terms of regenerative engineering. So in circular engineering, we go beyond simply minimizing harm. We aim excuse me, we aim to create systems that actually restore and enhance ecosystems. So this means designing technologies, materials, and processes that give back more than they take. We draw inspiration from forest cycles, which continuously regenerate soil and biodiversity. So coral reefs, which build complex habitats from simple materials, and natural regeneration processes that repair damaged environment. So the goal actually is not just sustainability, but regeneration. So helping the nature thrive alongside human pollution. So for the conclusion, or in the end, these are our key takeaways. The nature teaches us how to be efficient and circularly teaches us how to be responsible. When we bring these two together, we create a new engineering paradigm, one that is regenerative, resilient, and fully prepared for the future. And that actually ends my presentation. Thank you very much for listening. But before I end, I want to give you a quote that says, engineering the future means learning from the greatest engineer of all, which is the nature. Thank you very much once again. This is Maria Veronica Peña Florida, the International and Local Collaboration and Linkages Office of Cavite State University, thanking all of you, and may we have a good day ahead of us.
We will continue to the next speaker first. After that, we will combine question and answer in one session after the third keynote speaker.
Okay, I just want to thank again Universitas Wahid Hasyim. Is that okay? Before you introduce the next speaker.
Excuse me?
I just want to thank the Universitas Wahid Hasyim.
Oh, okay.
Before you introduce. Is it okay?
Okay, it's okay.
Okay.
Please.
So,
take
thank you so much. It's just a 1 minute.
Okay.
Once again, I would like to thank Universitas Wahid Hasyim, particularly the Faculty of Engineering, for championing conversations like this and for advancing global collaboration and sustainable technologies. I hope that in the next few minutes, as we explore the nature-inspired and cultural innovation, as we have this further discussion, we will see how biology and engineering together can drive a smarter and more sustainable and more resilient future. Terima kasih dan selamat pagi. Thank you so much,
Terima
ma'am.
kasih kembali. Yeah, thank you. Give applause. Okay, our next keynote speaker is leading international researcher and academic in advanced energy system. He earned his Doctor of Engineering from Kyushu University and has built an impressive career in Japan's top institution. He served as project researcher at the prestigious University of Tokyo before joining the Tokyo University of Technology, where he is currently an associated professor of Institute of Innovative Research. He also holds a part-time lectureship at the Tokyo University of Agriculture and Technology. His research trajectory from hydrogen energy system at Kyushu University to his current focus place him at the cutting edge of sustainable energy innovation. As an editorial board member and reviewer for several journals, he actively shapes the scholarly discourse in our field. Joining us today from Tokyo, Japan, it is my pleasure to introduce Dr. Engineering Muhammad Aziz. Dr. Aziz will share his talk entitled Carbon Capture in Catalyst for Circular Innovation in Industrial System. A warm welcome, please, for Dr. Muhammad Aziz. Please, virtual floor is yours.
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Very good morning. Selamat pagi to all of you. I don't know whether my voice can be heard clearly over there. Can you hear my voice?
Yes, it's clear.
Okay, thank you very much. Okay. Also, thanks to all of the committee, especially to the moderators, for introducing me well. Actually, so I'm Aziz from the University of Tokyo. So before starting my presentations, I just would like to share my slide first. Okay, can you see my slide over there? Does it work well?
Yes.
Okay.
It's visible.
Okay, so thank you very much. So for today, I just would like to talk about, and also I slightly changed the title for the talk today, and I just would like to focus more on the decarbonization technologies and also some strategies, especially in some industrial and also energy sectors. And we expect that this kind of decarbonization methods or strategies, I think, are very important for our future, especially for Indonesian case. So I think this talk also quite potential to be correlated with some issues currently Indonesians and also global issues. And before my presentation, I just would like to introduce our laboratory, and I think thanks for the introduction from the moderators. But I just would like to update my introductions first. That now currently I'm not in Tokyo Institute of Technology, but I have moved to Tokyo University or the University of Tokyo 6 years before. So my current affiliation is the University of Tokyo. And also we have about now currently about 18 students in total, including about 12 students, regular students, and also we are welcoming and also facilitating any kind of like visitings and also course provision students. And now we have about 6 students joining us as the visiting students. And also we have about 4 researchers. So in our labs, we have about 22 persons doing the research under my supervisions. And in case that you have any interest for further collaborations and also detailed research, I think you can also access our website over yours, epi.is.u-tokyo.ac.jp, or otherwise you can Google my names with the addition of the University of Tokyo. And also there are some topic research that probably correlated strongly with some of you actually. So in case that you have any interest, I would just like really warmly welcome to all of you for having collaboration with us. And we have some energy modelings in terms of the steady state, also the dynamic state, including also small scale, large scale, country scale, regional scale, or etc. And then we are also developing some elemental technologies for hydrogen productions, carbon captures. We call it as the chemical looping technology, which is pretty, I think, challenging technologies in the futures. But I think this is very important in case that we are talking about the decarbonization or carbon capture in the future. And also we are focusing also for the hydrogen storage. We are much more focusing on the absorption-based hydrogen storage. So we are now developing any kind of new structures, what we call as the triply periodic minimal surface structures for efficient hydrogen storage and also transportations. And then we have also hydrogen utilization, especially for not only for to be limited to hydrogens, but also it includes also some ammonia, and it is strongly correlated with some dedicated combustion and also co-firing or co-combustion technologies, including also in case of Indonesian case, I think ammonia and also coal co-firing. And then we have also some research related to the industrial decarbonizations. So we are developing some processes for clean iron and also steel makings, and also some cement industries, etc. And then we have also now developing some technologies for the energy storage, including the battery, and also some nano microscopic structures for the electrochemical devices, including electrolyzers and also fuel cells. Okay, that's all I think for my introductions, and from now on I just would like to move forward for our talk today. And we could see over years that now currently we are in the transitions period for especially for the energy sector. And when we are talking about the decarbonizations, we have four different pillars over here. Decarbonizations in the field of the electrifications or electricity sector. So I think this is the largest decarbonization that we can do in the future. And then also decarbonizations and the non-electricity sector. So we can also have over years including also some decarbonization in industrial sectors, including like steel making, iron makings, chemical industries, or etc. And then we have also some other issues related with the energy efficiency, energy productivity, energy conservations. And finally, also, in case that it's very difficult for us to do any kind of decarbonization and also to improve the energy productivity, then we can have or set up any kind of like scenarios for having the smallest carbon budget constraints, or minimally that we can reduce the carbon intensity from our activities. But the most important point over here is that when we are talking about decarbonization, we are not only talking that we are avoiding any kind of carbon-based fuels. So in my opinions, like fossil fuels or etc. is really potential. I mean, there are potential for all of us. So we cannot avoid for utilizing this kind of fossil fuels. But the most important thing for this one is that while we are consuming this kind of carbon-based fuels or fossil fuels, how much actually we can do any kind of offsetting, or we have any kind of responsibility with the carbon emitted from this kind of activities, from this kind of carbon-based fuel activities. So that's things that we need actually to develop in the future. While we are consuming this kind of fuels, we are emitting CO2, but we have also responsibility to capture and also probably we can utilize or recirculate the CO2 emitted from our activities. So currently, this is the big pictures about the CO2 captures. CO2 capture is very challenging, and I think all of you also know that CO2 is really, stable material or stable gas in our atmosphere. So it becomes slightly reactive when the temperature reaches about 800 or 850 degrees Celsius. But below that, basically CO2 is really stable, and to cut the bonding between the C, carbon, and also oxygen is really challenging, and also the energy activation is very high. So that's why the cost for the carbon captures is really challenging for all of us. And we could see over years that really it depends on the concentrations of the CO2 from the emitted or the exhaust gas. And we can understand over years that like for general power generations, when the CO2 concentration is about 20%, or probably can be less than 10% volume concentration or molar concentrations, the cost can reach about $80 per ton CO2 itself. But usually for much more concentrated power generation, including also the coal, I think usually the concentration is about 20%. So the cost is still about $50 to $60 per ton. But for the ambient air, because the concentration is significantly less than percentage. So usually it is just only 400 or 500 ppm. We could see that direct air capture over here, the cost is very expensive. It can reach about $250 per ton CO2 itself. So there are some technologies that we are trying to develop and also try to reduce the cost in the future. But most of them basically can be categorized into the pre-utilization or pre-combustions, in combustions, including also the oxy-fuel combustions, and finally also the post-utilization or post-combustion technology. So which kind of technology in the future that is really promising for all of us in terms of the technological maturity and also the cost? I think we need actually to have any kind of clear roadmap to develop and also to adopt this kind of technology in the future. Otherwise, offsetting technology or offsetting strategy to capture the CO2, I think that will be only the dream for all of us. So, okay, this is a kind of other topics correlated with the circular economy, because it is very strongly correlated with the carbon capture and also decarbonizations. When we are talking about the circular economy, means that we would like to optimize the circulations of the materials and the energy inside the systems. And otherwise also, in addition, also we would like to minimize the energy and also the material input, as well as also the output of the materials and also the energy. Means that what we would like to have over here is that maximizing the circulations of the materials and energy inside the society, and as well as also maximizing the economy and also minimizing the environmental impacts to our environment. So the main idea over here is we are starting from cradle, but we would like to end up with any kind of a cradle again, not the grave itself. But so minimally we have two different strategies over here, whether we would like to have any kind of like cascading utilizations, like in case that the materials and also energy has been utilized or consumed from one system or one process, then this kind of wasted energy and also wasted materials can also be reutilized again for other processing. So it means that at that times, mainly we can extend the lifetimes of the carbons in the total and the global system itself. So that's the things that we can do with the carbon cascading utilizations. And another method that we really expected is that carbon recirculation. So we can do any kind of recirculation of the carbons. So in case that, for the example, in case that we emit the CO2, then the CO2 itself can be converted back to the CO. Then in CO, carbon monoxide is basically the fuel itself. So the CO actually can be reutilized again as the fuel, and also sometimes also it can behave as the reducing agents for several processing, including also iron and also steel making. So this is the fungibility of the carbons. So I don't want to talk in details about this one, but the main idea over here is that whether we would like to just consume the carbons and we just emit the CO2, or we can have any kind of carbons and convert the carbons to non-carbon based fuels, including like the hydrogens. For the chemical energy, we just have two different options of the elements. The first is carbon, and the second one is the hydrogens. In case that we converted first the carbons to the hydrogens, then during the utilization we don't emit the CO2. So it means that we can have much more friendly environment compared to distributed carbon-based energy utilizations. So in this case, it's pretty much more easier to us to capture the CO2, the upstream process, because it's sometimes much more, large scale, and it is much more also much more economic in case that we can adopt any kind of much more bigger scale of the carbon capture technologies. And this is the in energy and also CO2. So I think we could see over years also that the CO2 also will increase in the futures. They are the big concerns. The big problems over here is that how far actually we can have the responsibility, and then also to adopt a strategy to capture the CO2, as well as also having any kind of strategy, economic strategy to massively adopt this kind of strategies. Okay, this is the decarbonization in the industry. So industrial sector is also very important, because as we could see over here is that some industries basically they are emitting extensively the CO2 itself, including some iron steel makings, cement productions, and also chemicals. They are the three top CO2 emitters, and also followed by some other industries. So like in case of Indonesia, we believe that like we have also iron and steel making, like Krakatau Steel, Camry, or etc. And then we have also some cement producers, and then also some chemicals, including also the ammonia. And as the information to all of you that the ammonia synthesis, ammonia producers is basically the largest emitters of the CO2 in terms of the chemical industry itself. So we need to have this kind of strategy. We need to map carefully, clearly about what is the emitters of the CO2 and how far actually we can reduce that. Yeah, that's together also with the other sectors, including also the energy sectors, transportation sectors, etc. So transportation also plays very important CO2 emitters, including also the shipping, heavy trucks, and also for the passenger cars, including our cars or etc. And also for the building also, especially for the Indonesian case, we are emitting CO2 when we are doing any kind of cooling activities. I mean, when we are cooling down our spaces, our rooms, actually, that's, I think, the biggest emitters of the CO2 itself. So, as I mentioned previously, that's another options for the fuels or chemical energy is the hydrogen itself. But as we could see for years that the hydrogen is largely available in its oxidized state. It is the water itself. It is not in the original state of the hydrogen itself. Yeah, there are some potential for the white hydrogen, which is the hydrogen itself available by the nature. But the problem is that the amount of the white hydrogen is basically pretty limited. So converting the CO2 to the hydrogen, I think, is very important in the future because, as I mentioned, that capturing the CO2 in a much more large scale or upstream process is really much more easier compared to capturing the CO2 when it is distributed, such as like transportations, our cars, our vehicles, or etc. I think it's really very hard to capture the CO2 from this kind of small scale systems. So why the hydrogen itself? Hydrogen is basically quite, it is clean when we are utilizing the hydrogens, and then it basically can be produced from different resources, including also the fossil fuels, renewable energy, or etc. And also the good things with the hydrogen also is that it is gravimetric energy density. This is the energy density per kilograms or per mass itself is pretty high, 120 megajoule per kilogram, which is the highest chemical energy owned by any kind of fuels. Yeah, that's below the nuclear energy, but actually for the chemical energy, hydrogen has the highest energy density. But the problem is that because it is the lightest materials in the earth, finally, its volumetric energy density is very low. I think that's the lowest one, only 3 watt-hour per liters. So it means that when we are talking about the hydrogen, we are always talking about how far actually we can effectively store the hydrogen itself. So this is some other characteristics of the hydrogens, but I don't want to talk in detail about this one. So as I mentioned, that gravimetric energy density is the best one. And also the flame velocity is pretty good. So it means that it is when we ignite the hydrogen, we can get very fast flames. So it's pretty good for certain utilization, including like jet engines and also for gas turbine or etc. And also the ignition range is pretty wide, from 4% to 77%, which is the widest ignition range on by any kind of fuels. Usually for any kind of fuels, usually they start from 10 to 30%, something like that, including the methanol or etc., gasoline or etc. But hydrogen has the widest one. Yeah, it can be any kind of challenges. It can also be any kind of problems. Why it becomes also the problem? Because it also deals with any kind of safety. So it means that although in lean and also rich conditions, hydrogen is potentially combustible. Okay, then the application of hydrogen and ammonia is basically quite wide. We are not only talking when hydrogen and also ammonia is utilized for our cars, for our vehicles, but also the largest consumptions of the hydrogens in the futures is projected to be for the power generations. So replacing the currently running coal and also natural gas based power generations, and then followed by any kind of industrial utilization. As I mentioned, that it also can be utilized for steel, iron making as the fuel, and also the reducing gas, and also for the cement productions, ammonia, or etc. And then the last one is for the transportation, and we are projecting for the transportation is that it's not only for the small scale cars, but we are targeting for any kind of aviations like the airplane, because for the airplane, as mentioned, that it really prefers for any kind of like high gravimetric energy fuels, including especially for the hydrogen itself, and then including ship and also large scale transportation like the car, like the trucks, train, buses, and etc. So this is some integration. I just want to skip it. So when we would like to adopt the hydrogen in this case, what we can do actually. So minimally we will have 3 different steps over here, including the pilot. So this is the introduction state, investment state, and that introduction stage of the hydrogen itself. Then the second one is the infrastructures or market developments. I think this is the most important stage for all of us. Once we have any kind of massive adoptions of the hydrogens in the country itself, we believe that what we are expecting is that we can, create any kind of hydrogen economy. We can learn from the success of the Brazil's several decades ago when they are adopting the bioethanol for their country. What really happens when we have discussion with the expert from the Brazil? They say that why bioethanol in Brazil succeeded, because when the governments decided for adopting the bioethanols, then they changed everything. So so massive adoption is very important, including also the regulations as well as the systems or etc. Finally, the economy of the bioethanol in Brazil can be created. So I think that's the same thing also when we are talking about the hydrogen. How far actually we are not only focusing on the Indonesian case or small case than the country itself, but also we are talking about the regional and also probably about the global market of the hydrogen itself. So we can finally reduce the total cost of the hydrogen production, transportation, and also utilizations. So this is a possible roadmap for the hydrogens. As I mentioned previously, that it's not only for the transportation, but in the futures we are targeting for this kind of utilization. And we believe that these kind of demands are much more bigger than the transportation itself. So this is the demand projections and the cost of the hydrogen. That's a problem also. When we are talking about the cost, the current cost of the hydrogen produced from any kind of natural gas is about 1.5 to 1.7 US dollar per kilograms. So what is the problems? When we are producing the hydrogen from any kind of renewable energy, now currently the price of the hydrogen production is about 2.5 US dollar per kilogram hydrogens to about 6 or 7 US dollar per kilograms hydrogens. So which is really much more higher than the conventional hydrogen itself. So finally, when we are studying this kind of hydrogens and also carbon captures together, my conclusion is that we cannot separate between the hydrogens and also the carbon captures. So in the futures, when we are talking about the hydrogens or about the renewable energy, finally we need also to talk about the carbon price. So finally, now for the information is that like for the economic cost for the carbon capture is about 20 US dollar per ton itself. But for the carbon tax, some countries, including also Indonesia, we have about 2 US dollar per ton CO2, which is the gap between the real cost for the carbon captures and the carbon tax or the penalty that we need to pay when we emit the CO2 is very huge. So we are expecting that in the futures, we can reduce actually the cost for the carbon capture, while probably the penalty when we are emitting CO2 can be increased. So finally, when we have any cost of the CO2 captures about 8 to 10 US dollar per kilogram, while the cost for the carbon tax itself can be increased about 5 or 7 US dollar per kilograms, finally we can have much more competitive cost between the fossil fuels, because in case that we use fossil fuels means we need to also pay the penalty for the carbon tax. While we are producing the hydrogen or we use any kind of renewable energy means that we don't need to pay the carbon tax. So finally, there will be any kind of fair competitions between them actually. So there are some also potential decarbonizations for our case actually. Deforestation is very important, I think. So as I mentioned that, and we have calculated about the potential for the deforestation in Indonesia, and in our quite rough calculation, we found that in case that we do any kind of forestations, the amount of the carbon which can be captured by our forest itself during the forestation period is pretty matched with the total amount of the CO2 emitted from our coal-fired power plants actually. So it is about 200 gigaton per year itself. That's very potential, I think, to do any kind of carbon capture by doing any kind of forestation, especially during our transition period until 2060 to reach minimally to reach a certain percentage of the carbon neutrality which is set by 2060. Okay, then we talked about the CO2 emissions in the in the industry or etc. But I think also I have some limited time, so I don't want to talk in detail about this one. So some potentials, including also for the for industry, especially for the steel making, iron making, chemical industries, cement production, or etc. But the problem is that for this kind of decarbonization industry is very challenging. But because what? Because it is also cost, and some industries or some companies, they are facing any kind of financial constraints about these ones. And also another thing is that the success story. So we need any kind of examples from successful company adopting this kind of decarbonization or energy efficiency inside the company. And so and the knowledge itself, the technical maturity, and also how far actually we can have any kind of some incentives from the governments, including also some probably some strategies and also regulations from the government itself. So there are some possible for decarbonizations actually, including also the electrification. By doing any kind of electrification means that we can create or generate the electricity from the renewable energy, and then the renewable, because electricity basically has the exergy 1.0 or 100%, means that all the energy from the electricity can be converted to any kind of other forms, especially the heat itself. And then the second one is, as I mentioned, also the hydrogen. Hydrogen is very important. Is very potential for decarbonizing in the industrial status, and also using any kind of biomass and also renewable energy, and also doing any kind of carbon capture and also carbon utilization. The problem with the carbon captures is that we are also facing problems with the sequestration or storage. The storage for the CO2 is very challenging. Some countries are demonstrating some kind of geographical CO2 storage, but the problem is that until now there's no country that can conclude that they can get any kind of stable CO2 storage, because we need the stability of the CO2 storage for very long time, like 1,000 years, 1 million years. So there's no leakage from geographical storage of the CO2 itself. Okay, so this is some journey, this is some potential, and I have mentioned also previously in the last slide. So another strategy is that also we are moving to any kind of 3D printing technology. So when we have any kind of like conventional machining, like milling or etc., finally we waste a lot of the materials itself. So using any kind of 3D printing, I think in terms of the energy perspective, it is really the energy consumption is very low as compared to any kind of conventional machining or etc. Okay, so this is still makings, but I think I have limited time, so I just would like to end up my talk. So for the steel makings, it is very potential because hydrogens can behave as the reducing agents, not only as the fuels. So it can replace the carbon-based or coke-based steel making itself. But the problem is that when we utilize the hydrogens, it is endothermic reactions, and which is pretty different with the carbon base. It is the exothermic reaction. So we need actually to compensate the heat required for the furnace itself. So basically, in case that we have hydrogen for that, means that we need actually to add the hydrogens to provide the energy itself. Okay. I think that's all for this man or etc. And that's all. I think thank you very much for all of your attention. So in case that you have any some points to discuss, I would like to welcome for all of you. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Daris, for that forward-looking and system-oriented perspective on turning carbon capture into an engineer for circular innovation. It's perfectly set the stage for our final keynote speaker presentation. And we have now heard 3 exceptional and counter lectures from process-specific decarbonization to system-level carbon innovation, and finally to nature-inspired foundation design. We will now open the combined discussion session for our last 2 speakers, Dr. Aziz and also Prof. Pena Florida. Audience, the question and answer box is now open to answer your question. Please specify whom your question is for. Let's see the chat box. There are so many questions at the chat box. The first, I will try to read this. The first question is for Ma'am Veronica. This is.
Hi, yes, ma'am.
Okay. This is from Arya Aciputra, Teknik Mesin UNWAHAS. He wants to ask, what are the biggest barriers to adopting nature-inspired and circular design in mainstream engineering?
Okay, so thank you for that question. The biggest barrier to adopting nature-inspired and circular design in mainstream engineering include, first is limited awareness and cross-disciplinary skills, higher perceived upfront cost, and difficulty possessing short-term return on investment. So many organizations are also constrained by existing manufacturing system, study chains, and standards that favor traditional materials and linear, as what I have mentioned earlier, the linear take-me, dispose model. And cultural resistance, of course, would also be a great factor to new approaches. And then limited curriculum integration, that's why education actually plays a great role in order for us to integrate this biomimicry in our educational system, and challenging in scaling bio-inspired prototypes for further slow adoption. So together, of course, these factors make innovative designs seem risky compared to familiar engineering solutions that we are all familiar. So I guess that could be the biggest challenge that we faced in order to adapt to these specific changes.
Okay, thank you for the answer, Prof. Fernie. And then the next question is still for Prof. Fernie. The first question is, this is from Siska Putri, Mechanical Engineering, UNWAHAS. The first question is, how can collaboration between academia, industry, and local communities accelerate adoption? And then the second question is, what policies or incentives are needed to support circular innovation at scale? This is from Siska Putri.
Okay, so for the first question on the collaboration between academia, industry, and local communities, collaboration, of course, since I am the director for collaboration, both local and international, collaboration, of course, creates a powerful feedback. Actually, it creates a powerful feedback loop, considering the academia, which provides scientific insights. We also have the creative design methods and testing capacity. In terms of industry, on the other hand, contributes to the real-world constraints, fabrication, capabilities, and pathway to scale. And of course, local communities also would be a great factor, because local communities ground the solutions in actual needs, materials, and cultural context. So these groups co-design or collaborate together. They could co-design pilots, they could also share data and iterate together nature-inspired and circular solutions that would become more practical, affordable, and of course, socially accepted. So these reduce risk, shortens development timelines, and ensures innovations, and not only technically sound, but also economically viable and community aligned. So that answers regarding the collaboration. So regarding the second on what policies or incentives are needed to support this circular innovation at scale is that circular innovation grows fastest. Of course, when anything would go fastest when policies reward resource efficiency and penalize waste. So governments can accelerate adoption through incentives such as tax breaks for using recycled or bio-based materials, grants for circular research and development. We could also have procurement programs that would prioritize repairable and low-waste designs and extend producer responsibility policies that require companies to take back and recover their products. And we could also create or produce clear standards for recycling, durability, life cycle assessments that could also help the risk investment. And with this together, these policies can create a supportive environment for designing for reuse, repair, and regeneration become the economic default rather than exception. So that answer, that gives, I hope that gives clarification to those two questions.
Okay, thank you, Prof. Pena Florida. And the next question, this is for Dr. Aziz. This is a question from Ilma, Chemical Engineering UNWAHAS. She wants to ask about, can we produce hydrogen from ammonia cracking? It is potential for commercial use. If it is potential, then what is the source of ammonia? As we know for today, still produce ammonia from syngas.
Okay, thank you very much for nice questions. So we must understand that ammonia is the hydrogen carriers. So basically, it is really possible to convert the ammonia or to decompose ammonia to hydrogen itself. So we can do any kind of cracking. So it is just very simple reactions. So it is the opposite of the ammonia synthesis process actually. So we can crack it, we can decompose it from the ammonia to produce the hydrogens, and that usually also this kind of strategy is done for in case that we are having any kind of ammonia-based power generations. The problem with the ammonia is that the combustion characteristics is not so good compared to the hydrogen itself. The ignition conditions and also flammability limits and also flame velocity, ignition energy, etc. I think it's really different with the hydrogen itself. So basically, we crack the ammonia into several percentage, like 10% or 20% to hydrogens, and then mix the hydrogen with the rest of the ammonia itself. So it means that we can improve the combustion performance of the blended fuels itself. Yeah. So when we are talking about the originality of the sources itself, for the hydrogens, not from the ammonia, because ammonia is produced from the hydrogen itself. So it means that how far actually we can have any kind of different sources for the hydrogen productions. Yeah, hydrogen can be produced from different sources. I mentioned that it can be produced from fossil fuels, including coal, natural gas, biomass, or etc., and also directly also from the electricity through electrochemical processes. So basically, in case we are talking about the processes, we can have any kind of electrochemical processes, so converting the hydrogens from the electricity produced from any other sources, including the renewables, and also thermochemical processes, including several systems, including like pyrolysis, gasification, chemical looping, or etc., and also biological conversion actually. So we can have any kind of fermentation technology for producing the hydrogen also. I think that's my answer. Thank you very much for your questions.
Yes, I think the answer is also a question from Dewi, and also she asked about the hydrogen production, the source from fossil fuel. Hydrogen production nowadays are still depend on the fossil fuel. Is there any potential production hydrogen that is not sourced from fossil fuel? So Dr. Aziz already answered this question, right? This is
Yeah.
Yes, we can get it from the fermentation and the other source. That's right. And then the other, oh. Nah, this is from Ilma already, and then this is for Ma'am Veronica Angga Diaz from Informatics Engineering. What we have to think over when we want to adopt the nature for the innovation in technology.
Thank you, Angga Diaz, for your question. So, when we are thinking, or if we want to adapt nature for innovation and technology, of course, we need to think beyond copying the biological forms or the aesthetic or the physical form of biology. So instead, we of course need to understand the underlying functions and principles that make the natural systems efficient, resilient, and regenerative. So what I'm trying to say is that, or what it means is that we need to study how organisms were able to solve problems, such as self-repair, energy efficiency, material optimization, and closed-loop cycle, and translating these strategies into design that would be efficient and effective.
Okay, thank you for the question. And the next question, this is for Dr. Aziz from KISKA, Chemical Engineering. What are the challenges and opportunity for chemical engineering in integrating CO2 capture unit with CO2 conversion to value-add chemical CCU? And how can the waste heat or byproduct from this conversion process be optimally utilized within local industrial symbiosis network? Please, Dr. Aziz.
Yes, thank you very much. It is very challenging, actually. As I mentioned previously, that CO2 is really stable materials. So when we need to react the CO2 with any, or convert the CO2 to any kind of fuels, means that we need to tackle down it is energy activations. But still, we have some opportunities. Like when we are talking about the methanol synthesis, it means that we are mixing or reacting the hydrogens with the CO2 itself. It can react, actually. It can be converted to methanol. And the big problems over here is that the energy consumption is very intensive over here. So what we need to do with this one is that how far actually we can reduce in terms of the chemical engineering. The first one is how far we can reduce its energy activations. And also, like for the methanol synthesis, the temperature is still about 250, 300 degrees Celsius. How far we can reduce that means that when we can reduce the temperatures, we can also utilize any potential waste heat, as you mentioned. So reducing the temperatures for the synthesis itself is also very key points over here. So we can utilize several options for the waste heat itself, like industrial waste heat or etc. So in case that we can reduce to about 200 degrees Celsius, I believe that there are a lot of sources of waste heat that can be utilized for that. So and also another challenge is that for the energy activation means that how far we can develop any much more economic catalyst for that. So that's also another challenge for the chemists and also chemical engineers, and also another challenge for the and opportunity for the chemical engineering is that doing any kind of like new process or developing any kind of new strategy for that using any kind of process integrations or etc. So we have done in our research, probably you can also check our publications of that we have integrated integrated several processes for carbon captures and also for carbon utilizations. So for the example is that when we capture the CO2, whether using any kind of conventional systems or any kind of chemical looping, or which is much more advanced than the conventional one, we can separate the CO2. And once we have separated the CO2 and we just created the methanol, and then methanol is utilized as fuel, I think that's very, very problematic, because the lifetime of the CO2 is very short. So what we introduce in the system is that we would like to convert the CO2 that we have captured to methanol first, and then methanol is converted again to olefins, and then olefins can be the material for the polymers. So it means that when we created any kind of or produce any kind of polymers, you can imagine that polymers is very, very important materials for our plastics or etc. So it means that when we can produce the polymer itself from any kind of like our separated CO2, then the carbon lifetime, the CO2 life cycle itself can be extended significantly to about 20, 30 years or etc. Or probably it can finally also can be stored in this polymer state. So I think we have very large opportunities over years. How we can dig this kind of opportunities, I think that's very important in terms of the chemists and also chemical engineering. Thank you very much for your questions.
Yes, that's inspiring answer, I think. And maybe this is the last question from Ahmad Abdul Jalil. This is for both two keynote speaker. The first question is for Dr. Aziz. What synergies exist between carbon capture technology and industrial symbiosis networking? I think it's almost the same with the last question.
Yes, I think it's pretty similar. So I think I don't want to repeat again. I think.
Okay. Thank you. And the next.
Thank you very much.
Okay. And the next question for Madam Veronica. I'm from Mechanical Engineering. How can mechanical engineer integrate biomimicry into product design for sustainability? I think okay. So this is the last question, I think, for our session today. And now we arrive at the last session. Yeah. On behalf of we will close this. Opening. Okay. We will close this session. From now, this is on behalf of Faculty of Engineering and Universitas Hasyim. I would like to extend our devout gratitude to our three outstanding keynote speakers for the invaluable contributor. Dr. Trirat Falkanaruh for detailed technical roadmap and bioethanol decarbonization, ground improvement industrial and academic experience, and then Dr. Engineer Muhammad Aziz for reframing carbon capture not as an end, but as a dynamic catalyst for circular industrial innovation. And then the last Profma Veronica P. Pino Florida for reminding us that the ultimate blueprint for sustainability is found in nature, and for inspiring a new paradigm for engineering design. Thank you for your generosity in sharing your groundbreaking knowledge and for the stimulating insightful discussion. To all our participants, thank you for your attentive presence and engaging question. You have been a wonderful and thoughtful audience. This concludes the keynote speaker session on the 5th National Seminar on Science and Technology and International Conference on Informatics, Mechanical, Industrial, and Chemical Engineering. We will now take a short break before proceeding to next technical parallel session. Please check the conference schedule for the time, and please give virtual applause for both our keynote speaker. Thank you. Thank you, and see you in the next session. Assalamualaikum warahmatullahi wabarakatuh. MC.
Universitas Wahid Hasyim sebagai salah satu perguruan tinggi swasta yang berlandaskan Ahlus Sunnah wal Jamaah merupakan salah satu perguruan tinggi Nahdlatul Ulama terbaik di Indonesia. 24 tahun berdiri, Universitas Wahid Hasyim memiliki 25 program studi dari 9 fakultas. Fakultas Ekonomi dan Bisnis, Fakultas Pertanian, Fakultas Keguruan dan Ilmu Pendidikan, Fakultas Agama Islam, Fakultas Ilmu Sosial dan Ilmu Politik, Fakultas Teknik, Fakultas Hukum, Fakultas Farmasi, Fakultas Kedokteran. Sebagai universitas dengan jargon intelektual yang berkarakter, dengan bangga, Universitas Wahid Hasyim meraih banyak prestasi dari tingkat nasional hingga internasional, baik dari bidang akademik, olahraga, agama, dan seni. Fasilitas yang memadai membuat ribuan mahasiswa nyaman menuntut ilmu di Universitas Wahid Hasyim. Sarana prasarana yang lengkap menunjang pendidikan seluruh mahasiswa di universitas ini. Hadir untuk seluruh kalangan masyarakat, Universitas Wahid Hasyim menyediakan banyak beasiswa. UNWAHAS semakin dicintai mahasiswa dalam negeri dan luar negeri. Bentuk kepercayaan seluruh elemen lembaga dan instansi terhadap Universitas Wahid Hasyim, kerjasama dalam negeri dan luar negeri, terlaksana sebagai penunjang lulusan terbaik dan terampil. Inilah wajah Universitas Wahid Hasyim untuk Indonesia sebagai perguruan tinggi yang berani unggul menciptakan generasi emas Indonesia dengan pendidikan yang berkualitas dan berkarakter. Kami Nahdlatul Ulama, kami cinta Universitas Wahid Hasyim. Universitas Wahid Hasyim, aswaja, muda mendunia.